Characters of a representation. Consider a representation gamma of a group G. That means for each element Gi of the group, there will be a matrix gamma Gi associated with it. Let the dimension of the representation be given by L. By that we mean that gamma Gi are matrices, square matrices of L. Then the character of a group element Gi, which we denote as chi of Gi, in a representation lambda, in a representation gamma, is defined as trace of the corresponding representation matrix. So here, the representation matrix of Gi in the representation gamma is gamma Gi, and therefore its character in this representation is defined as the trace of that matrix. Now, trace of a matrix is simply the sum of the diagonal elements of the matrix, and therefore this will be equal to sum over k running from 1 to L, where L is the dimensionality of the representation of gamma kk Gi, the diagonal elements of gamma Gi. The set of traces of all representation matrices of the group is called the character of the representation. So character of an element is defined by this. Now the character of the representation is defined as the set of all characters of the group element in that representation. The characters of an irreducible representation is called irreducible characters or simple characters. Now we discuss some of the properties of characters of representation. Suppose we have two elements which are conjugate to each other. So Gi and Gj are conjugate to each other. So that means there will be an element Gk of the group such that Gi will be equal to Gk inverse times Gj times Gk. Then if we take the trace of this, then the representation matrices of Gi and Gj are related in the following way. So gamma Gi will be equal to gamma of Gk inverse times Gj times Gk. Now since gamma is a representation, this will simply be the product of these matrices, gamma Gk inverse times gamma Gj times gamma Gk. Again, gamma is a representation, and therefore gamma Gk inverse will be equal to the inverse of gamma Gk. And that's what we have here. Now we need to find the characters of, or need to find a relationship between the characters of Gi and Gj in this representation. So if we compute the trace of gamma Gi, we will get the character of Gi. So that will be equal to trace of this object, this matrix. So trace of gamma Gk inverse times gamma Gj times gamma Gk. But now trace of ABC is equal to trace of CAB. So we can permute the matrices in the product cyclically so that the trace remains invariant. So we can take this to the left of the inverse of gamma Gk. So we will get this equal to trace of gamma Gk, then inverse of gamma Gk times gamma Gj. Now gamma Gk times its inverse is the identity, and therefore this will be identity times gamma Gj which is nothing but trace of gamma Gj. But that is the character of the element Gj in this representation. So we have established that if Gi and Gj are conjugate to each other, then chi Gi equal to chi Gj. Or in other words, elements that are conjugate to each other have the same character. So now we can think about conjugacy classes. A conjugacy class of a group is a collection of elements which are all conjugate to each other. Since they are all conjugate to each other, all elements in a class will have the same character. So a conjugacy class consists of elements conjugate to each other, and therefore all its elements have the same character. And therefore a conjugacy class can in fact be labeled in terms of the character of the conjugacy class. So if Ck is a conjugacy class of the group, all elements in Ck will have the same character, and we may denote this character by chi k. And suppose if this is a character in an irreducible representation gamma alpha, we may also put a superscript here alpha to indicate that it is the character of the class Ck in the irreducible representation gamma alpha. So another property is that equivalent representations have the same character. This follows straightforwardly because if we have two representations gamma dash and gamma, then for each group element we will have gamma dash Gi equal to some if S is some non-singular matrix, S inverse gamma Gis. So if these two gamma and gamma dash are equivalent, that means there exists a non-singular matrix S that satisfies this condition. So if I calculate the trace of gamma dash, which I may call as chi dash of Gi, which is the trace of gamma dash Gi, this will be the trace of S inverse gamma Gi S. But then because I can cyclically permute these matrices within the trace operation, I can take this to the left of S inverse, then S times S inverse is the identity matrix. Identity matrix times gamma Gi will be gamma Gi, and therefore this will be equal to trace of gamma Gi. So this will be equal to trace of gamma Gi, which is the character of Gi in the representation gamma, which we write as chi of Gi. So that means the character of a representation is the same in all equivalent representations. In gamma dash as well as in gamma, the character of a given element Gi the same. So we now consider one more property, which is that the character of the identity element in a representation is equal to the dimension of the representation. And this is also straightforward because the representation matrix of the identity in an n-dimensional representation will be the unit matrix of order n. And therefore the character of identity element in that representation will be the trace of the unit matrix, and that will be equal to trace of unit matrix of order n, simply n. And therefore the character of identity in an n-dimensional representation is simply n. Now we discuss orthogonality theorems for characters. Analogous to the orthogonality theorems for the representation matrices, we now consider orthogonality theorems for the characters. And the first orthogonality theorem says that if chi alpha and chi beta are characters of irreducible representations gamma alpha and gamma beta respectively of a finite group of order G, then if we take the product of chi alpha Gi star times chi beta Gi and then take the sum over all group elements Gi, that will be equal to G times delta alpha beta. So this sum will be equal to 0 if the representations are inequivalent irreducible representations. And if alpha and beta are the same, then sum will be equal to G, the order of the group. Now, this quantity is the complex conjugate of the character of Gi in the irreducible representation gamma alpha. So, the complex conjugate of chi alpha Gi. To prove this, we start from the orthogonality theorem of representation matrices, which says that if alpha and beta are inequivalent representations whenever alpha is not equal to beta, then it satisfies the following orthogonality condition, which says that sum over Gi gamma alpha Pm Gi star and gamma Qn gamma beta Qn Gi equals G by L alpha delta alpha beta delta PQ times delta Mn. Now, to relate it to characters, we first put n is equal to p and n is equal to q in equation 1.49, that is this equation. So we put m is equal to p and n is equal to q, and similarly here m is equal to p, n is equal to q, so that this becomes gamma alpha pp and this will become gamma beta qq. So now I can take sum over p and sum over q, and these sums corresponding to these matrices will give the corresponding characters. So summing over p and q with m is equal to p and n is equal to q, we will get this summation is there, sum over Gi, then sum over p of gamma alpha pp star. So sum over p running from 1 to L alpha, and that's because gamma alpha have dimension L alpha. So gamma pp alpha Gi star. So times, then I will have a sum over q also. So sum over q running from 1 to L beta, because these matrices are of order L beta by L beta, and gamma QQ Gi. And on the right hand side, G by L alpha delta alpha beta, then sum over P and sum over Q, P running from 1 to L alpha and Q running from 1 to L beta of delta PQ. Now with M is equal to P and N is equal to Q, this factor also becomes delta PQ. Now this is sum over Q of gamma beta QQ of Gi, which is nothing but the character of Gi in the irreducible representation gamma beta, which we denote as chi beta Gi. So beta representing the fact that it is a character in the irreducible representation gamma beta, and Gi because it's the character of Gi in that representation. Now in this sum, this is equal to sum over P gamma alpha pp Gi star, but this can be written as, take the sum first, pp Gi, then takes the complex conjugate. But this is nothing but the character chi alpha of Gi, the character of Gi in the irreducible representation gamma alpha. So this will be equal to the complex conjugate of this character. So which I may write as chi alpha Gi star. So that's what we have over here. So the result on the left hand side is that sum over Gi chi alpha gi the star times chi beta gi is equal to whatever is on the right hand side. Now the right hand side can be simplified because it's a summation over the Kronecker delta, and we see that each term delta P2 times delta P2 is non-zero only when P is equal to Q. So when P is equal to Q, this is 1 and this is 1. So their product is also 1. So this is actually the sum P running from 1 to L alpha of 1. Because whenever Q is different from P, this will be 0, which is equal to L alpha. So on the right hand side, we have G by L alpha, delta alpha beta, and this sum is equal to L alpha. So L alpha cancels with this L alpha, and the result is G times delta alpha beta. So this is the result that we wanted to prove. That is sum over Gi, and the complex conjugate of chi alpha Gi times chi beta Gi is equal to G times delta alpha beta. So, the result can be repeated here. Sum over Gi in G, then you take chi alpha of Gi star times chi beta of Gi is equal to G times delta alpha beta. Now, the character of elements of a given class will all be the same. And assuming that, if we denote the number of elements in a class Ck as Nk, this summation can be represented in terms of summation over classes only, because all elements in the class will have the same character in a representation. So we first consider the kth class and all those elements. So there will be Nk elements in that class. Then the character of all of them will be the same, and we represent the character as chi k, and to show the representation to which it belongs, we also have an index representing that. If it is in gamma alpha, the irreducible representation gamma alpha, we write it as chi alpha k. So the character of this class in the representation gamma beta will be written as chi beta k. So in this sum, considering the elements in class Ck, we will have Nk of them. All of them will have the same character. And for a typical element in that class, this chi alpha Gi star can be written as chi alpha k, then star. And in the representation gamma beta, we will have this equal to chi beta k. Now for all elements in that class, this term will be the same. So this product will be the same for all elements in that class, and there will be Nk such elements. So in the sum, the contribution will be Nk times this, and the summation over all elements of the group is now equivalent to summation over all such classes. So we just need to take the summation over classes running from k equal to 1 to C, where C represents the number of classes in the group. So this orthogonality equation in terms of summation over classes can be written as this, which is exactly what we have done here. So sum over k running from 1 to C, where C is the number of classes in the group, of Nk, then chi k alpha star, and chi k beta is equal to G times delta alpha beta. So now we have one more orthogonality theorem involving the characters, and in this case we consider the different irreducible representations of the finite group G. So for a given finite group, for a given irreducible representation gamma alpha, consider a class P of the group. Then in a given irreducible representation gamma alpha, the characters will be denoted as chi P alpha. So chi alpha P. So this corresponds to the character of the class P in the irreducible representation gamma alpha. By character of class P, we mean the character of any element in the class, because all of them will have the same character. So now we consider all irreducible representations of the finite group G, and then consider the characters of classes Cp and say some Cq. Then take the product chi P alpha star, then chi Q alpha, then take sum over alpha. That means sum over all irreducible representations of the group. So if R represents the number of inequivalent irreducible representations, then this sum will be equal to G by NP, where NP is the number of elements in the class Cp times delta PQ. So that means if P and Q are not the same, so they are different classes, then this sum is 0. If P and Q are the same, obviously NP is equal to NQ and delta PQ is 1, and the result would be G by NP. So we now have two irreducible representations, two orthogonality theorems concerning the characters of the representation. The first one is that sum over k running from 1 to C, where C is the number of classes of nk chi k alpha star and chi k beta is equal to G delta alpha beta. And in this case, the summation is over different classes of the group, and we have two fixed irreducible representations, and we expect this equation corresponds to a case when gamma alpha and gamma beta are inequivalent irreducible representations if alpha and beta are different. Now here in the second orthogonality theorem of characters, we consider two fixed classes of the group, so Cp and Cq, and then take sum over all inequivalent irreducible representations. So that also lead to an orthogonality relation like this. If classes are different, then this sum is 0, and if the classes are the same, then this sum leads to G by P. Whereas in this case, if the representations are different, then this sum leads to 0, and if the representations are the same, then sum is equal to G. We have been provided the proof of this theorem in this set of notes. And these characters also satisfy another important property, which will be used later in finding out the irreducible representations and finding the character table. Let chi k alpha represent the character of the class Ck in the irreducible representation gamma alpha of a finite group, and let L alpha denote the dimension of this representation. Then if Ni represent the number of elements of the group in the class Ci, then Ni Nj chi I alpha chi j alpha is equal to L alpha sum over k running from 1 to C, C being the number of classes of the group, of Aijk, and these are numbers, times Nk times chi k alpha. Now these numbers a, I, j, k are defined from the relation connecting the product of classes Ci and Cj. Remember the class product that we defined earlier. We take the elements of Ci and Cj and multiply all of them, and we so if a particular element of the group appears more than once, we keep them there in the product. And we have also seen in one of our earlier classes that the product of the classes contains complete classes, and therefore the result of this class product, class multiplication between Ci and Cj, will contain complete classes. For example, if a particular class Ck, one of the elements of a particular class Ck is there, all elements of the class will be there. And since we are allowing the repetition of group elements in this product, a particular class Ck may appear once or more than once, or it may not appear at all. So let Aijk denote the number of times a class Ck appears in the class product Ci times Cj. Then I can write Ci Cj as simply the sum over k running from 1 to C Aijk Ck. Symbolically, this means the class Ck, the elements of the class Ck appears Aijk times in this product. So to prove this property, we define a matrix Pi alpha where I correspond to the class index. So for a given class Ci of the group and for a given irreducible representation gamma alpha, we consider the elements A of the class Ci. Then in this representation, the representation matrix of A will be gamma alpha A. Then I take the sum of these matrices over all elements A in Ci. So sum over A in Ci and call it the matrix Pi alpha. So that is this definition. Now this matrix Pi alpha has a property that it commutes with all the representation matrices. To see that, we consider an arbitrary element B of the group and then consider the representation matrix of B in this irreducible representation gamma alpha, and that is given by gamma alpha B, and take its product with Pi alpha. So gamma alpha B times Pi alpha equals gamma alpha B times the Pi alpha is replaced by this sum. So sum over A in Ci gamma alpha A. Now this can be taken inside the sum. So the result is sum over A gamma alpha B and gamma alpha A. But since this gamma alpha is a representation, this is equal to gamma alpha BA. Now I can write BA as BA times identity, but B inverse B is identity. So I can write it as sum over A gamma alpha BA B inverse B. So this is gamma alpha of the matrix BA B inverse times the matrix B. Now since it is a representation, I can write it as the product of gamma alpha BA B inverse, and that is this, times gamma alpha of B. Now what is BA B inverse? A is an element of the class Ci, and multiplying it with from the left with B and from the right with B inverse produces one of the elements equivalent to A. But all elements equivalent to A are in the class Ci. So, in fact, B inverse is one of the elements of Ci. So, as I change A over the elements of Ci, I will be producing elements of Ci themselves. So, thus instead of taking the summation over A in Ci, I could instead take the summation over this object B inverse. This will also take me through all the elements in the class Ci. So we will give B inverse a name and call it D. Then in this summation, instead of taking summation over A in Ci, since D is also in A, we could take summation over D. So in that case, this will become D. And since B inverse is equal to D, that means B that has to appear over here. So B can appear as B itself. So doesn't matter. So in the summation, I can write it as summation over D. D is an element of Ci, gamma alpha D, then gamma alpha B. So this can also be written as summation over D in Ci, gamma alpha D times gamma alpha B. But this object is nothing but P alpha I. So the result is that gamma alpha B times P alpha I is equal to Pi alpha times gamma alpha B. Which says that Pi alpha is a matrix that commutes with all representation matrices of the irreducible representation gamma alpha. According to Schu's second lemma, if Pi satisfies this condition, it should be a multiple of the identity matrix. That multiple will be labeled as gamma alpha I. The indices alpha and I because we have alpha and I appearing here in P. So Pi alpha will be written as lambda alpha I times the identity matrix. But this is an identity matrix of order L alpha. Because Pi alpha is a square matrix of order L alpha times L alpha. As it is constructed from the representation matrices gamma alpha. We now try to find the value of this number gamma I alpha. For that, we take the trace of this equation. So trace of P alpha I is lambda alpha I times trace of this identity matrix. So this has dimensions, this has order L alpha, and therefore trace of this identity matrix is simply L alpha. Now trace of Pi alpha is simply trace of sum over A in the class Ci of gamma alpha A, which is nothing but sum over A in Ci trace of this individual matrices gamma alpha A. But this is nothing but the character of the element A in the irreducible representation gamma alpha. But now each of these element A is an element of the class Ci, and all elements in a given class have the same character. And that character is denoted by chi I. So we have a summation over A in Ci, and each term here is chi I alpha, the same term. And there are ni terms, nia's elements in the class Ci. So this is a summation of chi I alpha n times, which is n times chi I alpha. So the result on the left hand side is ni times chi I alpha, but on the right hand side that is equal to lambda alpha I times L alpha, from which I get this number lambda alpha I, which is ni chi I alpha by L alpha. And substituting this in this equation, we will get P alpha I is equal to Ni L alpha chi I alpha times the identity matrix. We now consider the product of these matrices P alpha I and P alpha J. So this is the P matrix corresponding to class Ci and this one corresponding to class Cj. And Pi alpha is nothing but, so P alpha I is sum over A in Ci gamma alpha of A, and P alpha J is equal to sum over A in Cj gamma, maybe let us call it B in Cj, then gamma alpha B. And taking this product, we will get this equation sum over A in Ci, B in Cj, gamma alpha A, and this one gamma alpha B. But these are representation matrices, gamma alpha, and therefore this should be equal to gamma alpha AB. Now, what is the product AB? A is an element of class Ci and B is an element of class Cj. And the product of them will be an element of the class product Ci Cj. And as I have told you earlier, Ci times Cj is sum over k aijk ck. So that means in the product Ci Cj, an element of the class Ck appears aijk times. So if I take all elements A in Ci and summation over all elements A in Ci, summation over all elements B in Cj, that will produce elements AB, which are elements of the class product Ci Cj, which will be an element of one of the classes Ck, and each of that element will appear aijk times. So instead of performing the sum individually over classes Ci and Cj, we could take a sum over the classes Ck, and every element in class Ck will appear aijk times here. So this sum can be rewritten as sum over k running from 1 to C, where C is the number of classes. And then if C is an element of the Ckth class, then the corresponding term would be gamma alpha of C, but C will appear aijk times as seen from this equation. So that corresponding term will appear aijk times. So and also I have to take sum over all elements in that class Ck. So this product Pi alpha, Pj alpha is simply sum over C in Ck gamma alpha C, but this will appear, each class Ck will appear aijk times. So I have to multiply its contribution with aijk. Then I have to sum over all classes, sum over k running from 1 to C. But this quantity now is nothing but Pk alpha from the definition of this matrix. So the result is that pi alpha times pj alpha is equal to sum over k running from 1 to c aijk pk alpha. Now we have an equation for pi alpha, which is ni by l alpha times chi I alpha times the identity matrix. So if I substitute that over here, I will have for pi alpha ni by l alpha times chi I alpha, then there will be an identity matrix here. Then for pj alpha, I will have nj by l alpha chi j alpha, then there will be identity matrix. Identity matrix times identity matrix is an identity matrix. And on the right hand side, I have sum over k running from 1 to c aijk, and for p alpha k, I will have nk by l alpha chi k alpha and the identity matrix here. So that equation is satisfied only if this number on the left hand side is equal to this number on the right hand side. Now cancelling one L alpha from here and one from the right hand side and taking this to the right side, we will get the desired result, that is Ni Nj chi I alpha chi j alpha, that is this, equal to, this goes to the right side, so L alpha sum over k running from 1 to c aijk nk chi k. So the result, this is the result that we set out to prove. This one. Now we can attach a geometrical meaning to the orthogonality theorems of representation matrices and the characters. To see that, we first note that the representation theorem for the orthogonality theorem for the representation matrices as the following form. We will have the inequivalent irreducible representations gamma alpha and gamma beta. Then we will have, say, p q of the group element gi, then take the star of that, then gamma beta m n of again gi, then sum over gi in group G is equal to G by L alpha, then delta alpha beta, then delta PM and delta Qn. So this was the orthogonality theorem for the irreducible representation matrices. So this result. Gamma alpha, gamma 2n. So that means given an element gi of the group, we can construct this matrix gamma alpha gi, and for each p and q, I can construct gamma alpha pq of gi. The group has if the group has g elements, I can construct these numbers gamma alpha pq g1, gamma alpha pq g2, and so on up to gamma alpha pq gg. So this is an ordered set of n numbers, sorry, g numbers, gamma alpha pq g1, gamma alpha pq g2, and so on up to gamma alpha pq gg. So we may consider it as a row vector in a g-dimensional complex vector space, because this gamma, alpha, pq are complex numbers. So in a complex vector space with elements like this, we can also define an inner product the following way. Gamma alpha pq inner product with gamma beta mn is equal to sum over, by the way, look, the indices for the components of this vector are g1, g2, g3, etc. up to gg. Or we may also consider these indices as the first one, second one, third one, etc. up to the gth component. So an inner product may be written as sum over I. So if we have two complex vectors in a g-dimensional space, and we denote them as a and b, and with the components a1, a2, etc. up to ag, and b1, b2, b3, etc. up to bg, then the inner product of a and b can be defined as sum over I running from 1 to g of ai star bi. Now here, instead of the vectors a and b, we have vectors denoted by gamma alpha pq and gamma beta mn. Then we can take a sum over I, and ai star will be written as gamma alpha pq star of gi, and vi is written as gamma beta mn gi. Instead of writing a sum over I running from 1 to g, we may also write a sum over gi in the set G, the group G. So this is an inner product in this space. So remember, for each irreducible representation alpha, each inequivalent irreducible representation alpha, and each value for p and q, where p and q will be a number starting from 1 to L alpha, because that's the dimension of the representation gamma alpha. And for each pq and alpha, we will have a vector which we denote as gamma alpha pq. And the components are gamma alpha pq g1, gamma alpha pq g2, etc. up to gamma alpha pq gg. So the components of this vector are labeled by the group elements here, or as 1, 2, 3, etc. up to g. And we can also define the inner product this way. But our orthogonality theorem says that sum over gi in G, gamma alpha pq star of gi, gamma beta mn gi is nothing but g by L alpha, then delta alpha beta, delta pm, and delta qm. There is a slight mistake here. So this should be delta pm and delta qn instead of delta pq and delta nm. So that means this quantity is equal to, so that is, this inner product is equal to g by L alpha, delta alpha beta, delta pm, delta qn. So that means this inner product is 0 unless alpha is equal to beta. So that means this and this should be same. And not only that, delta pm means that p should be equal to m. So this p should be equal to this. And this delta qn means that q should be equal to n. So that means this inner product is 0 unless this vector is the same as this vector. So that means So two different vectors, gamma, alpha, pq, are orthogonal to each other. And when they are the same, then their inner product is equal to G by L alpha. That is, if alpha equal to beta, P equal to M, and Q is equal to N, then their inner product is equal to G by L alpha. Otherwise, if they are different, and that is alpha and beta different means they correspond to different inequivalent irreducible representations. So the representation vectors corresponding to two different inequivalent irreducible representations are orthogonal to each other. And not just that, even if the irreducible representations alpha and beta are the same, if PQ is not equal to Mn, not the product PQ equal to product Mn, I meant P is equal to M and Q is equal to N, then they are orthogonal. So that means only when the representation vectors, only when we take the inner product of the representation vector with itself will we get a non-zero value. If we take the inner product of a representation vector with the representation vector corresponding to an inequivalent irreducible representation, the inner product will be zero. Or in other words, the representation vectors constructed this way are orthogonal to each other. Now, how many such vectors are there? Remember, if there are R irreducible representations, R inequivalent irreducible representations of the group, then alpha can run from 1 to R. Now, for each irreducible representation, gamma alpha, so there will be R of them. The dimension is L alpha. So P can run from 1 to L alpha and Q can run from 1 to L alpha. So if I construct vectors of this form, gamma alpha PQ, there will be R possibilities for alpha, L for each alpha there will be L alpha possibility for P and L alpha possibility for Q. So for a given alpha irreducible representation, the number of vectors of this form is the number of possible choices for the pair PQ. So P can take L alpha value, Q can take L alpha value. So the total number is L alpha into L alpha, which is L alpha square. So for a given irreducible representation, we have L alpha square vectors of this form. Now we have R such irreducible representations. So we just have to consider the sum of L alpha square for each of them. So the total number of vectors of this kind, the representation vectors, is sum over alpha running from 1 to R of L alpha square. Now each of these vectors, representation vectors, as we have just seen, are orthogonal to each other. And orthogonal vectors are linearly independent. And the number of linearly independent vectors in a vector space should be less than or equal to, or the maximum number of linearly independent vectors in a finite dimensional vector space should be less than or equal to the dimension of the vector space. Now, what is the dimension of the vector space? We look at the components here. So we have components labeled by the group elements. So if the order of the group is G, there will be G components, and therefore this representation vector is a vector in a G dimensional complex vector space. The number of such vectors is given by this, number of representation vectors is this, and the dimension of the space is G. Now the maximum number of linearly independent vectors in a G dimensional space is G. So obviously these are all, each of these vectors are linearly independent, and therefore this sum should be less than or equal to G. So we get the first inequality connecting the number of irreducible representations to the order of the group, which is given as sum over alpha running from 1 to r, L alpha square should be less than or equal to G.